Welcome to Chapter 3. This is the chapter on applications of derivatives. So, we're going to start off, and really over half the chapter is talking about graphing here. We're going to look at how do we graph functions, equations, anything that we have written out mathematically. How can we use derivatives to find out some key points about these graphs? Well, first off, I'm going to start talking about just what is a minimum or a maximum. I think you've probably seen this question before. But if I look at the first one here, I have one maximum and one minimum. Those are both local. A local maximum or relative maximum means that's the highest point in this localized area. Same, likewise, for the local or relative minimum. What's the absolute highest point, though? And the answer is, I'll give you a hint, the answer is not infinity. Infinity is not really a point. It's not even a number. There is no highest point. There's no absolute maximum or absolute minimum on this cubic function. It just keeps going down, at least if we're looking at the entire graph. Give me a minute to explain that comment. Over here we have a sine graph. There are lots of minimums and maximums. In fact, the highest point that a sine graph can ever reach, unless there's a transformation, is 1. But it touches that height of 1 over and over again. You could say that we have a lot of maximums. And when I say a lot, I mean an infinite number. Actually, each of those maximums, each of the crests on a sine wave, is going to represent the absolute maximum as well as the localized. In this localized area, that is the highest point. Over the entire graph, that is also the highest point. So it's okay to have more than one absolute maximum or absolute minimum, like this graph would also have. Down below, we have the seagull function because it looks sort of like when you draw seagulls in, second grade, or just any birds at all. But this function has one absolute minimum. We'll take a look at, finding things in just a moment with it in a different way. Both sides will continue to go up. No big deal. And the line, of course, has no maximums or minimums as currently defined. Well, now if we take a look at those exact same graphs, but we look at them on a different interval, everything can change. So let's say I would only like to look at part of the domain that's there. I'm looking from -2 to +3. What do I have in the way of relative extrema? What's extrema mean? Extreme values. Any really large or small. In other words, any maximums or minimums. Well, I still have a local minimum here and a local maximum there, but now what are my absolute values? It turns out that my absolute maximum is right here. That's no surprise. But since we're now looking at this interval, my absolute minimum is down here at 3, -15. When I suddenly looked at only an interval here, there is definitely one absolute minimum and one absolute maximum. I'll be honest, nothing changed about this interval for sine. The absolute minimum and maximum are still -1 and 1. There's not as many points where that occurs, but they are still there. However, here on this graph that was moving up to infinity, when I look at this interval, I definitely have an absolute maximum, or a global maximum as it may be stated. And even a line, a linear function, when I cut it and say I only want to look at this part, there is one highest point and there is one lowest point on this graph. And that's kind of the main point of this lesson here. This brings us to the idea of the extreme value theorem, another existence theorem that basically says, hey, we have these things, but I'm not telling you how to get them. The extreme value theorem is quite the formal statement, but essentially it's saying if you have something that's continuous on a closed interval, there has to be a maximum and minimum in that interval. There has to be a highest or a lowest point, whether it's the end point or something in between. So in the next video, we will look at the definitions for max and min, but mainly how to find